Transformers are among the most common devices found in the electrical field. They range in size from less than 1 cubic inch to the size of rail cars. Their ratings can range from millivolt amps to gigavolt amps. It is imperative that anyone working in the electrical field have an understanding of transformer types and connections. The two main types of voltage transformers are isolation transformers and autotransformers. Single-phase transformers. A transformer is a magnetically operated machine that can change values of voltage, current, and impedance without a change of frequency. Transformers are the most efficient machines known. Their efficiencies commonly range from 90% to 99% at full load. Transformers can be divided into three classifications: isolation transformers, autotransformers, current transformers. All values of a transformer are proportional to its turns ratio. This does not mean that the exact number of turns of wire on each winding must be known too. What must be known is the ratio of turns. NP, or number of turns in the primaries, or number of turns in the secondary up, or voltage of the primaries, or voltage of the secondary up, current of the primaries, or current of the second isolation transformers. This simply means that the secondary is physically and electrically isolated from the primary winding. There is no electrical connection between the primary and secondary winding. This transformer is magnetically coupled, not electrically coupled. This line isolation is often a very desirable characteristic. Since there is no electrical connection between the load and the power supply, basically the transformer becomes a filter between the two. Isolation transformers greatly reduce any voltage spikes that originate on the supply side before they are transferred to the load side. Some isolation transformers have a very simple ratio 1:1, meaning the input have the same ratio of turns as the secondary or output. Basic operating principles. As current increases from zero to its peak positive point, a magnetic field expands outward around the coil. When the current decreases from its peak to positive towards zero, the magnetic field collapses. When the current increases towards its negative peak, the magnetic field again expands, but with an opposite polarity of that previously. The field again collapses when the current decreases from its negative peak towards zero. This continually expanding and collapsing magnetic field cuts the windings of the primary and induces a voltage into it. This induced voltage opposes the applied voltage and limits the current flow of the primary. When a coil induces a voltage into itself, it is known as self-induction. Excitation current. There will always be some amount of current flow in the primary of any voltage transformer regardless of type or size, even if there is no load connected to the secondary. This current flow is called excitation current of the transformer. The excitation current is the amount of current required to magnetize the core of the transformer. The excitation current remains constant from no load to full load. As a general rule, the excitation current is such a small part of the full load current it is often omitted when making calculations. Mutual induction. Since the secondary windings of an isolation transformer are wound on the same core as the primary, the magnetic field produced by the primary windings cuts the windings on the secondary also. This continually changing magnetic field induces a voltage into the secondary winding. The ability of one coil to induce voltage onto another coil is called mutual induction. The amount of voltage induced in the secondary is determined by the ratio of number of turns of wire in the secondary to those of the primary. Distribution transformers. A common type of isolation transformer is the distribution transformer. This type of transformer changes high voltage of power company distribution lines to the common 240/120 volts we use at home and in many businesses. The secondary side can be divided into a 120-volt system by supplying a neutral from the secondary side or center tap. This creates a 240 volts or 120 volts secondary side. Transformer core type. Several types of cores are used in the construction of transformers. Most cores are made from thin steel punchings laminated together to form a solid metal core. Transformer inrush current. A reactor is an inductor used to add inductance to the circuit. Although transformers and reactors are both inductive devices, there is a great difference in their operating characteristics. Reactors are often connected in series with a low impedance load to prevent inrush current. Transformers, however, can produce extremely high inrush currents when power is first applied to the primary winding. The type of core used when constructing inductors and transformers is primarily responsible for this difference in characteristics. Magnetic domains. Aeromagnetic materials containing tiny magnetic structures in their molecular materials known as magnetic domains. These domains can be affected by outside sources of magnetism. If the polarity of the magnetic pole is changed, the molecular structure of the domain will change to realign itself with the new magnetic lines of flux. This external influence can be produced by electromagnets as well as permanent magnets. Autotransformers are one-winding transformers. They use the same winding for both primary and secondary, and a selector to select the proper voltage or terminal points in order to connect to the proper voltage. Transformer rating. Most transformers contain a nameplate that lists information concerning the transformer. The information listed is generally determined by the size, type and manufacturer. Almost all nameplates will list the primary voltage, secondary voltage, and kVA rating. Transformers are rated in kVA and not kilowatts because the true power is determined by the power factor of the load. Determining maximum current. Nameplate does not list the current rating of the windings. Since power input must equal power output, the current rating for a winding can be determined by dividing the kVA rating by the winding voltage. For example, 1 kVA rating and a primary voltage of 480 volts. If we know the secondary is 120, then to determine the maximum current that can be supplied by the secondary, divide the kVA rating by the secondary voltage. Transformer impedances determined by the physical construction of the transformer. Factors such as the amount and type of core material and wire size to construct the windings, the number of turns, and the degree of magnetic coupling between windings greatly affect the transformer's impedance. Impedance is expressed in percentage and with the letter Z. Join me tomorrow where we will talk about three-phase transformers and the different configurations used. As always, please like, share and subscribe.